Welcome back to the Deep Dive. Our mission, as always, is pretty simple. We take a huge pile of research and boil it down to what you actually need to know. And today we are plunging into, I think, the single most important foundation for modern computing, the resource building blocks of Kubernetes.
Yeah, this is a really crucial one. If you're starting your cloud-native journey, maybe you're looking at the KCNA certification, well, this is Module 1. It's where the vocabulary itself starts to shift, and if you don't nail down these first few concepts, honestly, everything else gets confusing fast.
Okay, so let's just dive right in. When we say Kubernetes resources, I feel like the first mental trap for people is hardware. CPU, RAM.
Right, physical machines.
But in the world of Kubernetes, the word resource means something totally different.
It does. We have to reset that definition right now. In Kubernetes, a resource is an API object. That's it. It's a piece of text, usually YAML, that describes the desired state of your system.
So you're not touching hardware, you're just writing a wish list.
I mean, in a way, yeah. You're declaring what you want. You tell Kubernetes, I want 3 copies of this app. And then the system's job, its only job, is to make reality match your declaration.
So if we're learning the vocabulary to write that wish list, what's the absolute first word we need to know? The most fundamental object?
That would have to be the pod. The pod is the atomic unit in Kubernetes. It's the smallest deployable thing that the system even recognizes.
But why? Why create the pod? Why couldn't Kubernetes just manage, a Docker container directly?
It's all about context and a shared environment. So yes, a pod very often holds just one main container, but its real power, its purpose, is that it can hold multiple containers that have to work together as a single unit.
Okay, so that's the peas in a pod analogy I keep hearing about.
Exactly. And when they're in the same pod, they are guaranteed to be on the same machine, and they share everything.
What's everything?
Their network, for one. They have the same IP address, so they can talk to each other on localhost. They can also share storage volumes. This is perfect for something like a sidecar pattern where you have your main app and then a little helper container next to it doing logging or monitoring. They live and die together.
Okay, that structure makes a ton of sense. But you mentioned there's a critical flaw with pods. What's the danger of just running a single naked pod by itself?
The danger is simple, and it's fundamental to understanding Kubernetes. Pods are ephemeral. They're mortal. If a pod crashes, app error, node dies, whatever, it doesn't come back. Kubernetes will not resurrect it. It just stays dead.
So if you launch a pod by itself, you've launched a single point of failure with no self-healing.
Yeah.
That's a huge mental shift.
It absolutely is. The whole system is built expecting failure, which leads us right to the next layer of resources that exist only to solve this one problem.
Okay, so if the basic unit of work is designed to die and stay dead, what gives us the resilience we need for, a real production website?
We move up a level of abstraction to the replica set. This is where stability comes in. A replica set has one very simple, very strict job. Make sure a specific number of identical pods are running at all times.
So it's like a supervisor doing a constant head count. If I say I want 5 pods,
it makes sure there are always 5. If one of them dies, the replica set controller sees the count is at 4, knows the desired state is 5, and it immediately spins up a new one to replace it.
And this happens automatically?
Instantly. That's the self-healing. It doesn't fix the broken thing. It just replaces it with a new one.
Okay, that's powerful. But here's the thing. You mentioned we almost never actually touch a replica set directly. We use something called a deployment. If the replica set is doing the hard work of self-healing, why do we need this other thing, this deployment, managing it?
That's the critical question. The replica set is, it's reactive. It only cares about maintaining the current state. The deployment, on the other hand, is the manager of strategy. It's about managing change.
And by change, you mean updating my app, like going from version 1 to version 2.
Exactly that. Imagine you have 5 pods running V1, all managed by one replica set. If you just changed that replica set, it might just kill all 5 at once to start the new ones.
Which would mean downtime. A lot of downtime.
Right. The deployment prevents that chaos. It's much smarter.
So walk me through it. How does a deployment handle a rolling update without causing an outage?
Well, when you tell the deployment you want to move to version 2, it doesn't touch the old replica set at first. Instead, it creates a brand new replica set for version 2. It slowly starts scaling that new one up. Maybe it adds one new V2 pod. Once it sees that new pod is healthy and running,
then it kills one of the old ones.
Exactly. It then scales the old V1 replica set down by 1. It's this carefully managed one-for-one handover. It maintains the total number of pods the whole time, so your users never see a disruption. And if that new V2 pod fails, It just stops the rollout and can instantly roll back.
So, just to recap for everyone listening, the pod is the disposable worker. The replica set is the supervisor, making sure enough workers show up. And the deployment is the CEO, planning the strategy for how to hire new workers and retire old ones without shutting down the factory.
That's a perfect analogy. That hierarchy is key.
Absolutely. Okay, so our app is running, it's stable. But in a big company, a single Kubernetes cluster could have hundreds of apps from different teams. How do we keep things organized? How do we stop the dev team from accidentally breaking the production environment?
We do that with namespaces. The easiest way to think of a namespace is as a virtual cluster inside your real physical cluster. It's a way to partition everything.
And what's the main benefit? Is it just for organization, like folders?
It's organization, but it's also for security and scope. Resources in the development namespace can't see or touch things in the production namespace by default. It provides that critical isolation. You can have a dev, a prod, a staging namespace, or even one for each team. It stops people from stepping on each other's toes.
A necessity, for sure. Okay, moving from organization to configuration. This is Security 101, but we have to say it. You never, ever hard-code passwords or credentials into your container image.
Please don't. A leaked image becomes a leaked set of keys to your entire kingdom. Kubernetes gives us two specific resources to solve this by decoupling your configuration from your code: ConfigMaps and secrets.
And I'm guessing the difference is pretty obvious from the names.
It is. Secrets are for sensitive data. Passwords, API keys, TLS certificates, anything you need to keep encrypted and secure. ConfigMaps are for everything else. All the non-sensitive configuration, like environment variables, theme settings,
Yeah.
maybe a file that just says background color blue.
So how does a pod get access to that data? Does Kubernetes just copy-paste it in?
It's a bit more elegant. It's called injection. In your pod's definition, you say, I need the data from this secret or this config map. And Kubernetes can make that data available to your running container in a couple of ways, either as environment variables or can mount them as files that your application can read from the file system.
So that injection is the key. That's the decoupling.
Absolutely. Because now, if you want to change that background color from blue to red, you just update the config map. You don't have to rebuild and redeploy your entire application image. It's a huge operational win. It prevents that classic mistake of a developer hard-coding a production database password into a test build. This whole architecture is designed to avoid that class of error.
That really drives home why this matters. Okay, we have our app. It's resilient, organized, secure, but we're back to that core problem. Pods are mortal. Every time a replica set replaces a pod, that new pod gets a brand new random IP address.
Yeah.
So how does anyone find it?
And that is the exact job of our last foundational resource, the service.
The service provides the stability that the pods themselves can't.
Precisely. A service gives you a stable permanent IP address and a stable internal DNS name for a group of pods. That address never changes no matter how many times the pods behind it are crashing and being replaced.
So when my deployment does a rolling update and slops out all 30 of my pods, the other microservice that's trying to talk to my app never even knows. It just keeps talking to the stable service address.
That's the decoupling right there.
Right.
And the service does more. It's also an internal load balancer. It knows which pods are healthy and ready, and it automatically distributes the traffic across all of them.
That's fantastic. Are there different types of services depending on who needs to get to the app?
Yes, a few key types. The most common one you'll see is cluster IP, which is an internal-only address. It's for services inside your cluster talking to each other. Then you have things like node port and load balancer, which are designed to expose your application to the outside world, but the core idea is always the same: a stable entry point.
I love that mental model. The deployment is like the back-of-house manager, making sure the staff is always there and working, but the service is the front door. It's the permanent address on the building that never changes, even if the staff inside the pods are constantly changing.
It creates that clean separation. The consumer doesn't need to know about all the chaos and self-healing happening underneath.
We've covered a ton of ground here. For anyone studying for the KCNA, we've just nailed the 6 core resources. We have the bricks, our mortal pods, the supervisor, making sure there are enough bricks, the replica set, the manager with the plan. The deployment, we organize them in different rooms using namespaces. We give them their instructions with blueprints, config maps, and secrets. And finally, we give the whole building a permanent front door, the service.
That's the entire foundation. And the really interesting thing, the bigger idea here, is that this entire complex, resilient architecture, it all exists because of that one single decision at the very beginning.
That the pod is ephemeral.
Exactly. The system is designed from the ground up to embrace failure. It assumes components will fail, and it's built to react. The pod is the atom of failure. The deployment is the molecule of resilience. And that raises a really important question for you, the listener, to think about. What kind of profound changes does your team need to make to go from the old mindset of trying to keep one server alive forever to this new world where you design systems assuming failure is just normal?
That is a phenomenal thought to end on. It's not just about learning the tools, it's about adopting the philosophy that failure is the norm, not the exception.
Indeed, the technology really dictates the philosophy here.
Well, this has been an excellent deep dive. Thank you for making these foundational concepts so clear.
My pleasure. Go forth and declare your desired state.
We'll see you next time on The Deep Dive.